Okay, so as we start at, this is x to the 1/2 in the bottom, right? So rewrite this. It's still going to be the integral from 1 to 4, but x divided by x to the 1/2 is going to become x to the 1/2.
Oh, I did do that.
You have to.
Shoot.
Minus, there's going to be a coefficient of 2, and when you take that x up there, it's going to be x to the negative 1/2. And then officially times dx.
Okay. I get it now.
Okay. So, yeah, on that one, we do not have a way. Yeah, there's no way other than you need to divide it. So rewrite it. So we did x divided by x to the 1/2 minus 2 divided by x to the 1/2. Gosh. Okay. Integral of x to the 1/2. Add 1 to the power. So it's 3/2. Dividing by 3/2 is 2/3 x to 3/2. Minus, adding 1 to the power makes it positive 1/2. Dividing by 1/2 is multiplying by 2, and we already have a 2 there. So minus 4x to the 1/2. Evaluated from 1 to 4. And then it's just a matter of plugging it in.
I did integral.
So plugging in 4 first. 2/3 times 4 to the 3/2 minus 4 times 4 to the 1/2. Minus, put this whole next part in parentheses, and it's 2/3 times 1 to the 3/2 minus 4 times 1 to the 1/2. Okay. On this 4, are you guys good with 4 to the 3/2? It's the square root of 4, which is 2, cubed, which it makes it 8, right?
So
16.
And then you're doing 8 times 2/3,
16.
so 16/3,
Oh yeah.
minus 4 to the 1/2, square root of 4, which is 2, times 4, which is 8, minus, parentheses, 1 to any power, times 2/3, makes it 2/3, minus 1 to any power, times 4, minus 4. You can do this a couple of different ways, okay? I sometimes will just take, think of this all as one thing and take like pieces. I know I've shown you several different ways. You really just kind of go with what your brain sees here. That's my best suggestion. So I kind of see 16/3 minus 2/3 as 14/3. Negative 8 minus negative 4. So it's negative 8 minus negative 4. So negative 8 plus 4 is negative 4. And then in order to do 14/3 minus 4/3, I'm doing 14/3 minus 12/3, which is 2/3. Again, getting that 2/3, okay? We could have made this all thirds if you want, okay? We could have made this all thirds, but you also have to go with what does your brain see, what's going to be easiest without a calculator. So, okay. That was a good review from yesterday. Okay, total change concepts and explaining the integral in real world terms. So, if f of t represents the rate at which your 401k changes in value over the month of January. Okay, so notice right here, right? Yeah. 401k is something that you would take money from your paycheck usually and deposit into that 401k. And it's, yeah, econ is exactly where you would go with this because it's money that's it's usually invested. It's not just compounding interest or something. Usually your 401k is on the stock market essentially. So.
That's what I was
Okay.
taught. I was taught so many things. It's crazy.
Okay, so FFT represents the rate. So units of FFT. Wait, I'm trying to remember how these blanks work. These blanks confuse me. Oh, okay. So we're doing units of FFT, units of DT, and units of FFT DT. There we go. Took me a moment. So units of FFT. FFT represents the rate at which your 401k changes in value over the month of January. So if we talk about this, label. What is the label there of your units as it changes? What's changing? Dollars. Now think rate per day. So this one is dollars per day. Okay. DT. Well, yes, it tells us the variable we're integrating with respect to. I also think of it kind of like delta T, so like DT. So change in time, which is days, or day. Well, that means F of T dt. That is, F of T is the function we're talking about is money. So that is your money portion there. Okay. Now, as you look at that specific integral, the integral of F of T dt from 1 to 31 represents the total change in what? One to 31 should be a hint.
Money in 1 month.
Yeah, in January.
You're right, because it's 1 to 31. There's 31 days in January. So it's over the course of January. So total change in what's changing? The value of your 401k over the month of January. And I guess it is in dollars I have written down. So the value of your 401k in dollars for the month of January.
I just think that 401k that you could only get up to 401,000.
I don't think that's what it means.
I've always wondered kind of like what
But that was like when I was
but-
like younger. I saw because K always meant 1,000.
Yeah, I don't know. Now, see, and I will say, my husband has a 401k. He's also Chrysler and more in the business world. In the teaching world, the equivalence of a 401k is a 403b. So I have a 403b that does the same thing as a 401k. So,
Gotta love Chrysler though.
so now, difference between a 401k, 403b, other than different business world versus education world, I don't know. Mrs. Fernung might know, but I don't know. So, okay. We got it all? I think we got it all there. Okay. B. If R of T represents the rate at which your pizza changes temperature in a 475 degree pizza oven 5 minutes after the pizza had been placed into the oven to cook. Okay, so kind of what we did earlier. The integral from 5 to 20 of R of T dt represents the total change in
Temperature. Over the time.
over what time?
Wait, after 5 minutes of putting it in till 20 minutes.
Okay, from T equals 5 minutes to 20 minutes. And what kind of change is this in?
Degrees.
Degrees
Fahrenheit.
Fahrenheit, if we want to be specific, yes. Okay, so notice it tells us that R of T represents a rate. Okay, we're integrating a rate per the normal. and it talks about pizza change temperature. So this represents the total change in temperature of your pizza in degrees Fahrenheit from T equals 5 to T equals 20 minutes. Okay? You're going to have to deal with me writing small because I have this whole page squeezed onto one because I was trying to get all 3 sets of notes in here for all 3 classes. So I'm limited on pages. But when you're doing something like this, get the labels in there. Mention that it's this, not just the change over time, it's specifically 5 to 20 minutes. Use those boundaries and label those boundaries. And then once the temperature of your pizza changing, what is that unit that's changing? Okay? Question or no?
Yeah, would it be valid to like put temperature parentheses in degrees Fahrenheit of your pizza?
Yeah. Yeah, it doesn't have to be written in this exact form. Those are the pieces you need to get into. But, yeah. No, it wouldn't have to be word for word. Okay. You and your friends are planning to buy a ticket to your favorite music group, the Newtons. Interesting. Everyone wants to hear their latest hit. Why integrate? If A of T represents the rate at which students are arriving at the ticket window, and P of T represents the rate at which they buy their tickets and enter the concert, then. So you guys got why integrate. Did you get the Newtons?
Yeah.
Okay.
But why integrate can be like I can take it as social injustice.
Okay. Anyways, so example 1. The integral from 1 to 5 of A of T dt represents the what?
The rate of students.
Go back up here. What's it say A of T is?
The rate at which students are
Arriving at the window.
Okay. And when we integrate that rate, so it's going to be the number of students arriving at that ticket window.
in minutes.
An hour?
Why would you be 5 hours?
Yeah.
Does it ever specify? It doesn't.
Never
No.
specifies the time.
It must just be a logic thing.
I don't think I'd show up 1 minute before a concert.
Well, I know, I kind of agree, but on the flip side, you don't show up 5 hours
I
before a
know.
concert either. So it's minutes according to my notes. Okay? I don't know how you're supposed to assume that necessarily.
Maybe
but-
it's like a really, really large concert. You know how like people
Yeah.
show up to games 5 hours early?
Well, actually, it doesn't say. It just says,
It doesn't say how. It just says
it doesn't say before the concert.
it could be that 5-minute window.
Yeah. It doesn't say, now that I look at it, it doesn't say,
Time. Well, it doesn't really.
it's just
say.
the rate at which they are arriving at the ticket window and the rate at which they are buying their tickets and entering the concert. It doesn't say what that 1 to 5 is in reference to.
This could be an hour to 55
So-
minutes.
But yeah, so just, 1 to 5 though. You can't change labels there.
Well, I mean, like, that could be the 5.
Oh, okay, I see what you're saying. Yeah. So, what is this? So, the change in A of T, so that's going to represent the number of students. And what are they doing?
Oh, right.
Arriving.
They are arriving. And I have, on mine, I have it written as they are arriving to get in line, because they're arriving at the ticket window, so you are getting in line. I think you could say arriving to get in line. I think you could also just say arriving at the ticket window. Okay. I think both would be, arriving to get in line. And I have mine written as from 1 less than or equal to T less than or equal to 5 minutes. Okay. The minutes I think is just kind of assumed. But in that, from 1 minute to 5 minutes, wherever that timing starts. Okay? The integral from 1 to 5 of p of t dt, what does that represent?
The rate or the
When they buy their tickets
the
and
number of people buying tickets.
yeah.
Okay, so it's the integral of the rate at which they're buying their tickets. So the number of students that are buying tickets or have bought tickets, and what else?
Entering this.
Enter the concert. And that is also from 1 to 5 minutes, right? So number of students that buy tickets and enter the concert from 1 to 5 minutes. Now keep in mind, here I wrote a joint integral. 1 less than or equal to t less than or equal to 5, right? Could we have written it like we wrote up here from t equals 5 to t equals 20? Yeah, there's not one set way you write that. Okay? That is meaning that t equals 5 to t equals 20 is the same idea as the 1 less than or equal to t less than or equal to 5. So there's not a right versus wrong way of how you have to write that. So, yes?
I always get confused on how to know when to use the equal to or just the plain less than.
This one, because 1 and 5 are the boundaries, I would say equal to. Because we're going from 1 to 5.
Okay.
So. Okay. A of t minus p of t.
The
Number of students arriving minus the number of students that buy tickets and enter.
Okay. Now, technically, a of t minus p of t are not integrated, yes? So technically, it's still the rate at which those things are happening, right? So it's the rate of the students arriving minus the rate at which they buy their tickets and enter the concert. What effect is that on the line?
The rate of the line is
Or
Increase.
increasing, yes? Because as more students arrive, the line gets longer. But if you have more students that are getting their tickets, entering the concert, the line's going to shrink, yes? Just depends on how those rates are working there.
Depends on how many people are in.
So I have it now. The rate at which the line is increasing or decreasing, that works. That's good. I have it also, though, as the rate at which the line is growing or shrinking. Okay, so you can throw in those other words, too. Again, lots of ways to express these answers. The rate, the line is shrinking or growing. Okay, the integral from 1 to 5 of a of t minus p of t dt represents the total change in,
So it's only the first one integrated or
no, they're both.
Okay.
In my opinion, this would be appropriately written with parentheses there, because the d of t is after the other one. I don't know. In my opinion, the parentheses should have to be there, but you don't always see them there. So,
but the dt at the end kind of signifies.
exactly. And that was exactly the clue, is the d of t being after the p of t signifies it's both. So,
Would that be the number of students in line?
okay. Number of students in line, the length of the line, right? Because it's basically, this was the rate the line is shrinking or growing. So if we integrate it, it's the number of students in line, or in other words, the length of line. So I have the length of line in students on the interval 1 to 5. So the length of line in students, maybe of students, oh well, on 1 less than or equal to t less than or equal to 5 minutes.
And we still have 3 more pages.
I'm not done with this page. Don't rush me here. I know, we're not going to probably get everything done, but. Okay. D, recall that velocity, v of t, represents your velocity where the positive direction is to the right. Okay? Velocity, so 1, velocity is a rate at which what is changing?
Speed.
Position.
Oh, yeah.
Position.
Dang it. But I didn't know if it was like tricking us. It was the other way around. It was like acceleration. But speed.
Now, no, because, yeah, velocity is the derivative of position. So it's the rate at which position is changing. Now, the integral from 5 to 50 of v of t dt represents the total change in position on what interval? 5 to 50. So that's going to be the first blank. So in position on, and here I have brackets.
Oh,
So-
my goodness.
5 to 50. And we don't have a label, so I'm just using units. I've just mixed it all up here, aren't I? Now, in all honesty, this is probably what she did in the answer key also.
She drives me
When I-
crazy.
But here's the thing. It's good to see the options. And that's why I think she does it. And that's why I copy what she does on that sense, because otherwise I would get stuck and use the same one all the time. But here I can address the issue of, oh, there's options. Okay, so total change in position on 5 to 50, which has a special name in math called
Displacement.
displacement, or net change is also what you'll hear it in terms of in math. Displacement, or I have or net change in parentheses. Likewise, A of t is the rate at which blank is changing,
Velocity.
because acceleration is the derivative of velocity, so it's when velocity is changing.
I'm a little mad that none of them are speed. That makes me upset. Now we have 3 pages left.
Yeah. Okay. Don't worry about it. Just go.
10 minutes per page.
Moving along. Okay. Now I can read this better. Yeesh. So far, we have seen that when given f of x equals the integral of f of t dt, f of t has always been the derivative of f of x. In the next examples, we want to explore some special cases where f of t may or may not be the derivative of f of x. We want to find a general rule for evaluating expressions, such as d dx, so the derivative of the integral of a to g of x of f of t dt. Okay, and so this goes into that, the special case of why we can't just say, because technically when it's the derivative of an integral from a constant to a variable, you just plug that variable in. That's fundamental theorem of calculus part 2. But it's not always going to be that way. And so these are the special cases. Okay? So, I have a bunch of, yeah, I'm not going to write all those notes in. Okay, let's look at example 1. So find the derivative in 2 ways, and then we're going to basically, are they always going to be equal then? Okay? So, number 1, we're doing f of x equals the integral from pi to x of cosine t dt. So if we just integrate this by hand, Okay. What is the integral of cosine t? Sine of t, yes. So this is going to be sine of t evaluated from pi to x. Okay, this is what we learned yesterday, yes. What do? Sine of x minus sine of pi, upper limit minus lower limit. And what is the sine of pi? 0. So here we get f of x is equal to sine of x. Okay? How do I want to do this? Are those middle schoolers?
Probably.
I guess Mr. Summers has middle schoolers right now.
In their shackles.
Okay, and then the second part says find f prime of x. So what do we find f of x to be? We found f of x to be sine x, yes? Is this how I want to do this? Yeah, okay. F prime of x, derivative of sine x is cosine x. Now, what are we checking? Does little f equal f prime? Now, where was little f? Do we realize where little f was? Little f was over here. Because remember, the setup is always capital F is going to equal, so that stands for antiderivative. It's the antiderivative of little f. Okay?
So would you say no?
I'd say yes.
Well, what is f of x?
Cosine of x.
F of x is cosine x. What is f prime of x? Capital F prime of x. It is also cosine of x. So do they equal?
Check.
They do. F of x does indeed equal
I'm confused.
f prime of
Because
x.
it's t.
That's just a variable.
T is the variable that was used there. We're talking respect to x. So if you say f of x instead of f of
So-
t, you just switch out the variable.
Okay, so then that over there like doesn't matter.
It's just, I mean, that was f of t. So if we're going to talk about, okay, what was f of x, it just says switch the t for the x. Okay? Okay, so in this case, f of x does indeed equal capital F prime of x. And so that rule where you do d dx, the derivative of the integral, the pi to x cosine t dt. Oh, wait, I didn't want to put, shoot. I was trying to do general and I got, come on. Let me erase what I want to erase, or don't. You know, be difficult. Sorry. So d dx of the integral pi to x, but I wanted to generalize and say f of t dt is indeed going to equal f of x. Now, what this is, notice, my lower bound is a constant, pi is a constant, yes? My upper bound is a variable. And that's this case number 1, okay? And this is fundamental theorem of calculus part 2, okay? So that does indeed work here. Okay. Let's try another one. F of x equals the integral from 0 to x cubed of square root of 1 plus t dt. This again is a integral where upper bound is a variable, lower bound is a number. You ready to integrate? Now, square root of 1 plus t. That can be written as 1 plus t to the 1/2. 1 plus t to the 1/2. Yes?
Yes.
Okay. So now when we go to integrate that, we have something raised to the power of 1/2. Add 1. So 1/2 plus 1 is going to make it 3/2. Divide by 3/2, which is multiplying by 2/3. Now, why are we doing this when there's a parentheses here? Why does it still work? What would be the derivative of 1 plus t?
1.
It's still just 1, right? So is there going to be a chain rule issue?
No.
No. Okay. So this is going to be 2/3 1 plus t to the 3/2 evaluated from 0 to x cubed. Okay. Do some plugging in. Plug in x cubed first. So 2/3 times 1 plus x cubed to the 3/2 minus 2/3 times 1 plus 0 to the 3/2. Did you say you're going to leave it there? Only thing I can really clean up, there's not really much you can clean up other than the very end. Sorry. Had a sneeze, went away. So 2/3, 1 plus x cubed, raised to the 3/2, minus 1 plus 0 is 1. 1 to the 3/2 is still 1. Times 2/3 makes it
2/3.
2/3. Okay, that's fun. Okay. Now, we want to find f prime, capital F prime of x in this column. Except I should probably write out what f of x is. So we have that to look at, don't I? What did we just find f of x to be? 2/3. Okay, let's derive. F prime of x. 3/2. Multiply out front by 2/3. 3/2 times 2/3 is 1. Cancels. Then 1 plus x cubed raised to the 3/2 minus 1 is 1/2.
And then that's just.
And then you have to do the derivative of the inside.
Chain rule.
Times 3.
So times the derivative. So this was derivative of something to the 3/2 times the derivative of something. The derivative of 1 plus x cubed is 3x squared. Then I agree. Minus the derivative of 2/3, which is minus nothing. Okay.
Does that look like it matches?
I can clean this up a little bit and just say 3x squared times the square root of 1 plus x cubed. What do we, so we want to know, does f prime of x match f of x? What was f of x?
1 plus t to the
Square root
1
of 1
half.
plus 2.
Yeah. F of t was 1 plus t to the 1/2, or in other words, the square root of 1 plus t.
Is that what that
Sorry, I have my glasses on.
So f of x would be the square root of 1 plus x.
I can't see it.
Capital F prime of x is 3x squared square root of 1 plus x cubed. I don't know about you guys, but f of x does not match capital F prime of x. We are just going to ignore Mario. Okay.
We don't want him in forensics.
Okay.
That's much.
So,
That's a good one.
there was an example where you had a lower bound constant, upper bound variable. It did not work. Okay, so these again are special cases. Example 3. Difference here is upper and lower bound are functions. Okay, so let's see what we have here. Keep in mind, what's f of t going to be? F of t is going to be sine t. Okay, what do you know? Oh, wait. Why did I do that?
Did it wrong.
Why did I do that? Oh, that's why I did it. Okay,
I was talking about something.
sorry. I glanced at my notes and I was trying to remember why I did this. Officially, so our fundamental theorem, fundamental theorem of calculus does not technically apply when upper and lower bounds are both variables.
Danny.
Okay,
Hi.
so with that in mind, what I ended up doing here, and this is what I was checking, is I ended up breaking this up into 2 integrals. If you remember that property where if they have one boundary in the same, it's still the same piece. So I broke this up into the integral from x squared to a of sine t dt, and then plus, and now since a was the upper boundary and a is just a random number, we're going to go a to cosine x of sine t dt. Okay? Now,
That looks like a 9.
officially, when you integrate, your lower bound needs to be the constant. So that first integral needs to,
Be negative.
it's going to flip and it's going to be negative. So it's going to be the negative of the integral from a to x squared of sine t dt plus the integral from a to cosine x of sine t dt. Okay. I'm ready to integrate finally. What is the integral of sine t? Okay, so the integral of sine is negative cosine, right? Because the derivative of cosine is negative sine. There's no negative there, so it's negative cosine, but we do have a negative out front of this first one, yes? So it is going to be negative cosine t evaluated from a to x squared. Plus, now the integral of the next sine t is actually negative cosine t evaluated from a to cosine x. Okay. Evaluate your integral pieces here. Wait a minute. Why did I put a negative in here? We even talked about being positive, didn't we?
Yes.
So why did I put a negative in there?
I thought it was wrong.
No,
I was just like, Miss Doctor wrote it down. It's probably right. It's fine.
Yeah.
No. Don't assume that.
Was
No,
not
I'm
even
Do not assume that.
I'm assuming that.
Okay, sorry. My apologies. Because we talked. The integral of cosine, or the integral of sine is negative cosine. It's a negative of a negative, so it should have been positive. Okay, now we're plugging in. Cosine of x squared, cosine of the upper bounds, minus cosine of the lower bounds, which is a. Now,
What did I do?
how do I want to do this? Minus, this is cosine of the upper bound. So minus cosine of cosine x. Now, remember, we are subtracting here, yes? Or we're plugging into minus cosine. So this is going to be
Oh, shoot.
minus negative
So plus.
cosine of A. So exactly, plus.
So your cosine A, negative cosine A cancel.
Yes. So the cosine A's, minus cosine A plus cosine A, are going to cancel. So we are at capital F of x is cosine of x squared minus
Cosine
cosine of cosine x. Okay. If capital F of x is cosine of x squared minus cosine of cosine x. Capital F prime of x.
Is it plus? Oh. Oh, never mind. Never mind. Sorry.
Okay, no, you're fine. Okay. I've made my mistakes today, so call me, please. Okay. Derivative of cosine of x squared.
negative sin.
Derivative of cosine of something is negative sine of something. Times the derivative of something.
2x.
So derivative of x squared is 2x. Minus the derivative of cosine of something.
Negative sin.
Negative sine of something.
Negative sine of something. So can I go ahead and say
Yes.
plus sine of something? What's my something? Cosine x. So it's sine of cosine x
Times negative sine.
times the derivative of something. The derivative of cosine x is negative sine x.
Oh my god.
Okay. Negative sine x squared times 2x. I could just write that as negative 2x sine of x squared. And then minus, I can say sine of x times sine of cosine x. Why are we even questioning this one?
I think it matches, guys. Looks pretty similar to me.
So does this match this?
No.
F of x does not match capital F prime of x. Okay, so the warning there kind of is just beware. They're not always going to end up matching. I know. That page definitely took more than 10 minutes.
Yeah.
I'm trying to scan. I should have pre-prepared and I didn't.
23 pages.
Okay, now,
11 minutes left.
can you see the need for chain rule in some cases? And that's kind of where we just came from, okay? When you do f of g of x, you guys remember how to do the derivative of something like f of g of x? So what I would call a composition derivative. It came up on that derivative homework you had. But in order to do the derivative of f of g of x, you're doing what? F prime of g of x times g prime of x, the derivative of the inside, right? Okay, so that's your chain rule that we're talking about, okay, when we talk about a composition derivative. So looking at something like that. General form for fundamental theorem of calculus, part 2. Okay, the examples we just came through. Right here, here's the one where the lower bound is a constant. Here's the one where both pieces are functions. Okay, so with that in mind, let's see. this top one, okay, when the lower bound is a constant, that's what we just talked about. That's what we already know, because when you're doing the derivative from a constant to a function, you plug the function in, so it's plugging g of x into f. So it's f of g of x, but then you have to remember to do the derivative of the inside, so derivative of g prime of x. Now the difference here, not constants, but both bounds are functions. Or when we talk about functions, both bounds involve variables. How's that? Okay, they involve variables. With that in mind, okay, basically you're doing the top piece, plugging the top piece in, so f of g of x times the derivative of the inside, minus, and then you're plugging in the bottom piece. Do you see that? So it's f of h of x times that inside derivative, okay? If we look at 4 real quick, find the derivative of f prime of x given f of x is the integral from 0 to x squared of e to the t squared dt. Ooh, I don't know why it's a tongue twister for me, but so we're trying to find the derivative. Okay, the derivative, if we're doing the derivative of this, the derivative of the integral, they basically undo each other, right? So it's e to the t squared. What are we going to plug in for t? X squared. So it's e to the x squared squared, if you will. Obviously, I'll clean up that x squared squared in a moment. Times the derivative of x squared,
2x.
which is 2x. What is x squared squared?
X to the 4th.
X to the 4th. So I can rewrite this as 2xe to the x to the 4th. Okay?
That's not a lot.
Okay? 5. Evaluate the integral
It's possible. It's not possible.
if possible. It's not possible because it says that, and you guys are just too smart for that. But why is it not possible?
Because there's no.
What's true about denominator?
It can't be negative. Wait.
It can't
Be 0.
be 0.
And x
Well,
will
it can't equal 0.
Okay? X can't be 0 because it's in the denominator. What do you notice about these boundaries?
0's in between.
And
0's in that boundary, isn't it? Okay, so on -3 to 6 interval, the 2 to the x term doesn't exist. It exists from -3 to 0 and 0 to 6, but it doesn't exist the whole time. So the integral cannot be evaluated as is. Big thing is because it's not continuous on that interval. Okay? So let's see. 2 to the x is not defined at x equals 0, which is on -3 to 6. Okay? So integral cannot be evaluated okay. Keynote I'm going to put here, not continuous at x equals 0. Must be continuous. And when we say must be continuous, it must be continuous on the interval we're talking about. Okay? Could I do this integral if 0 wasn't included? Yes. If this was just 1 to 6, there'd be no issue. Okay?
put a D on evaluated.
Really.
Thank you. You know, catch my
Forgets
drift.
those a lot.
Okay. On 6, it's the integral from 0 to 4 of 2x minus 5, of the absolute value of 2x minus 5. Okay, I'm obviously not going to have time to talk about the whole thing here, but the issue you run into, absolute value is a
V.
V. Okay, this absolute value V does this at 2.5. Okay, what you would have to do, and again, I'm not going to have time to talk about this, but we would have to do the integral from 0 to 2.5. Do you see where I'm going with this? Plus the integral from 2.5 to 4.
How do you
Now.
know if it does that?
Because I know what absolute value looks like.
I mean, like, how do you know it's at 2.5?
2x minus 5 equals 0.
Yeah. Okay. Now, with this in mind, do we know how to integrate an absolute value? No. So what shapes do you see here? With a little work, could we make that happen? We would have to. Okay? I'm out of time right now, so I'm not going to go through the details there. I don't remember what's in homework that might correspond to that and get us in trouble, but we'll deal with it, okay? You can, keep in mind, you can look at the notes, yes? The notes key is also online. Integrating a piecewise, if you flip to the next page real quick, integrating a piecewise, you're going to have to evaluate each of them individually. And that's kind of what we were just talking about, is breaking into pieces here.
So like from -2 to 0,
Mm-hmm.
0 to 1, it looks like.
Well,
and
actually, you can do -2. You can actually just do 1. That's not a hard point. So you can do
but I
that.
thought because it's 0, you couldn't do it there.
0 was just because x was in the denominator of that 1.
Oh.
That was just a one-time thing.
Oh.
Yes.
Okay? And then we would do 1 to 4. And that's because there's this discontinuous part.
If it's a derivative, though, you wouldn't be able to do 0, right? That was like the graph derivative. That would be it.
That'd be a whole other story.
Oh.
Now, integration with a calculator. Have I talked about how to integrate on the calculator yet?
Yeah, we've done it.
We've done that? Okay. That's why I was stressing. I was like, oh no. Because that's exactly what 8 has to do with, is the calculator. And the bell's going to ring on me, isn't it? So, if f is an antiderivative of this fraction, such that f of 1 is 1/3, find f of 0. Well, the idea is you can do this integral from 0 to 1 of this function. Am I saying we know how to do that? No, this would be the calculator. But what's the idea? When you integrate this, you integrate it, and then you're going from, when you plug these values in, it's f of 1 minus f of 0. Does that make a little sense? Well, here's the deal. What do we know? F of 1 is 1/3. What am I trying to find? F of 0. Can you get this value with a calculator?
Yes.
Yes. Could you find f of 0?
Yes.
Does that make sense? Because f of 1 is some big long decimal, and you can do that on the calculator. Okay, so those are some highlights. Sorry. I don't know. Do what you can. I need to open the homework key. I do know that. Eesh. A lot of it, I think, will be integrate. I mean, just practice integrate. It is. So, lots and lots of practice. And right now, I'm going to open that answer key. Because if I don't do it now, it's not happening.
That's how it is.